And welcome to lab number 2. In lab 1, you looked at position and velocity graphs when the velocities were constant. You were also introduced to the concept of acceleration. For this lab, we'll discover how objects accelerate, what the relationship between acceleration and velocity is, and we will calculate acceleration based on a velocity graph. We'll start out by looking at the velocity time and acceleration time graphs of an object speeding up as it moves away from the motion sensor. We could try to do this with a cart being pushed by a hand, but that would be hard to make a smooth graph that way. Instead, what we'll use is a constant speed fan to drive the cart. With the present setup, the cart will be pushed by the fan away from the motion sensor. I've programmed the computer to start recording the data when the cart moves 15 centimeters away from the motion sensor, and to stop recording when the cart is 1 meter away. The data we collect then will be just the motion of the cart. All right, so what I'm going to do is I'm going to go ahead and do the start run. I'll start the fan, and then I will start recording, and you'll be able to see the position, velocity, and acceleration graphs. So let's go ahead and get started. I turn on the fan, and then I start recording. And there's the run right there. Oh, let me go turn off the fan too. Okay, so let's start off with the graphs that we see. And let me move the legends a bit so you can actually see it. And then because of some artifacts within the software itself, I'm going to apply a little bit of smoothing. First to the velocity graph, and then to the acceleration graph. There we go. And now to the acceleration graph. All right. So my question, let me go ahead and ask a few questions. All right, question 1-1. First of all, sketch the graphs that I've just made into your lab book on page 35 and then answer the questions. Question 1-1, how does the position graph differ from the position graphs for a steady or constant velocity for the motion that you observed in lab number 1? Just as a bit of a comparison, let me decrease the time scale and you'll see something a bit more interesting. If I decrease the time scale, then what does the position graph look like? There we go. Take the position graph. What kind of graph does that make? Does that look like a straight line, or is there some kind of curve to it? Question 1-2. What features of the velocity graph, what feature from your velocity graph signifies that the motion was always away from the sensor? Well, remember, what's the direction away from the sensor? How have we designated that? Is that positive or negative? Question 1-3. What feature of your velocity graph signifies that the cart was speeding up? And how would the graph of motion with a constant velocity differ? So take a look at your lab number 1 graphs, and you should be able to make that comparison. And question 1-4, during the time that the cart was speeding up, is the acceleration positive or negative? Well, let's take a look. Here's where the cart was speeding up. Is the acceleration on the positive side or on the negative side? How does speeding up while moving away from the detector result in this sign of acceleration? Question 1-5. How does the velocity vary in time as the cart speeds up? Does it increase at a steady rate or in some other way? Question 1-6. How does the acceleration vary in time as the cart speeds up? So look at the acceleration. How does that change in time? Remember, we're looking overall. I put some smoothing on it. Let me take some of the smoothing off and we may be able to see a little bit better. Does the acceleration change over time in the time range that it moves right in this region right about here? Does it really change? Question 1-7, the diagram on page 36 shows the positions of a cart at equal time intervals as it speeds up. Assume that the cart is already moving at time 0. At each indicated time, sketch a vector above the cart that might represent the velocity of the cart at that time while it is moving away from the motion detector and speeding up. Are the vectors getting longer, shorter, or keeping the same length? On the whiteboard, I've drawn the three carts, or rather the carts at various positions, starting with the motion sensor on this side and the cart moving in this direction. Now, in each time interval, as the cart moves in, say, half a second, it's going to travel a certain distance in half a second. If the cart is moving faster, it will travel a greater distance in the next half second, and then it'll move an even greater distance in the next half second. So what I can do is I can draw a vector that represents the velocity by just drawing a velocity arrow like so. Since it's a greater distance, well, actually what I can do is I can draw an arrow from here to here, because that's the distance that the cart travels in a certain amount of time. Then I can draw an arrow from 2 to 3, because that's the distance that the cart travels in the second amount of time. And then I can draw this arrow from here to here, which represents the distance that the cart travels in the third amount of time. These are all equal amounts of time, so therefore these are all going to be equal velocity arrows. Now question 1-8 is, show how you would find the vector representing the change in velocity between the times 2 and 3 seconds in the diagram. Let's take a look. At 2 seconds, here's the arrow. At 3 seconds, here's the arrow. So let's try this. Let's stack them. Let's take the first arrow, draw it like this. This represents the velocity at, this represents the velocity at time 1, or time 2 seconds. This will represent 0 velocity, 0 meters per second. Then this arrow is the velocity at time 3 seconds. I'm just going to draw an arrow with the same length. Okay? Now the question becomes, how can I represent the change of velocity from here to here? And we can represent the change of velocity by drawing an arrow from the head of V2 towards the head of V3. That's the change in velocity in that time interval. So as you can see, the direction of the change in velocity is in the positive direction. It's in the same direction as the velocity V2 and the velocity V3. So, just to recap. First, we draw the vector at 2 seconds. Then below it, starting from the same position, we draw the vector at 3 seconds. The change in velocity is a vector drawn from the head of the first vector to the head of the second vector. In other words, how did you get from the first vector to the second vector? Based on this vector, what is the sign of the velocity? Now let's go ahead and do activity 1-2. We'll repeat the experiment, but this time we'll make the fan blow harder. Answer the prediction 1-1 on page 37, and I'll go ahead and run the experiment. To do that, I'm just going to turn the fan on at a faster speed. So I'm going to resize the picture. I'll move the camera so that it looks at, right? So, change the velocity of the fan, so now it blows faster. We will go ahead and start recording. There we go. And turn the fan on and release it. And there's the data. Okay? so sketch this line on your axes on page 35 using a dashed line. Let me go ahead and show the previous run as well so you can do a comparison. So what's the difference between the two? Here's run 2, here's run 2, here is run 2. Let me put some smoothing on the acceleration graph of run 2. And you'll see something. There we go. Okay, so now comes the questions. First question. Did the shapes of the velocity and acceleration graphs agree with your predictions? How was the magnitude of the acceleration represented on a velocity time graph? 1-10, excuse me. How is the magnitude of the acceleration represented on the acceleration time graph? Okay, so what's the major difference? Simply put, on the acceleration time graph, we see that the line for acceleration is higher than the line for the acceleration in run 1. In run 1, the acceleration was around 0.3 meters per second squared. For run 2, it was somewhere around 0.5 meters per second squared. The slope of the velocity line is steeper than in run 2 than the slope of the velocity line in run 1. And as we can see, it took a much shorter amount of time to cover the same distance between run 1 and run 2. Run 2 took about, it looks like, if I look at the graph, about 0.3 of a second less to travel the same distance. All right, that finishes up investigation 1. The next video will be investigation 2.